My name is Yerramsetty, and I'm a software engineer on the infrastructure team. Today, I'll be talking about cloud cost optimizations and how you can use FinOps and FinOps practices to reduce your AWS cloud costs. Today, I'll also touch briefly on how you can use AI powered tools like ChatGPT, Claude, Gemini, and Llama to help you reduce the cloud cost. I'll also touch briefly on the AI agentic approach using LangChain and True AI, where you can build your own agents that will help you with the cloud cost optimization process. I'm excited for this talk. So let's just get started. Some introductions. I'll be going through introducing what is a cloud native cost optimization, what are some of the cost drivers in cloud native platforms, what are some of the resource management techniques, some container and serverless optimization, some storage and data management, monitoring and cost observability, what is FinOps, a cultural approach to cost optimization, and then I'll deep dive into leveraging prompt engineering and FinOps to drive cloud efficiency. So let's get started. So the first thing is like, what is a cloud native platform? The cloud native platform is a platform that lets you build and deploy applications seamlessly on the public cloud. It can be on any container orchestration platform like Kubernetes, ECS, or EKS. You have AKS for Azure Kubernetes Service or GCP. So whatever the public cloud may be. So those are called as cloud native platforms. So this is where you deploy your applications. And these environments tend to be dynamic and complex in nature because setting up requires like you need to set up a VPC, you need to set up a security groups, you need to set up a whole bunch of virtual networking, and also you need to deploy and maintain the virtual machines, which we call EC2 instances. So each cloud providers have their own terminology. At the end of the day, it's just like virtual machines. So some of the statistics show that 30% of the cloud spending is wasted due to resource mismanagement. And this tends to be true because you often have engineering teams who spin up these instances, spin up the new databases for testing purposes. They tend to build new features, which are sometimes abandoned because the business doesn't require them. And they're never turned off or decommissioned properly. This is the source of like increasing cloud cost. And the objective of this presentation covers strategies for optimizing costs in cloud ready setups and also enabling financial responsibility without compromising on agility or scalability. So let's get started. So, what are some of the cost drivers in cloud native platforms? The first thing that comes to our mind is virtual machines, compute. So compute comes in various different forms. It can be like EC2 virtual machines that are managed by us, or it can be like a Lambda, like function as a service that can be managed by AWS. So for the virtual machines that are managed by us, like the cloud providers give us a variety of virtual machines. They're like the smaller virtual machines, and some are like very resource intensive, CPU intensive, or memory intensive virtual machines. Now, each have their own pricing model, and like they tend to be more expensive as they scale vertically. Now, the serverless executions are a tricky bit because it lets you execute a function as a service, but if you call that function like 100,000 times, it tends to get expensive. So there's no benefit of using function as a service when you're calling it frequently. So the next type of the cost driver is storage. Storage comes in three forms. You have block storage, you have object storage, and you have RDS databases. Now, the object storage is S3. So S3 is pretty scalable. So we tend to fill up our S3 buckets. We have a bucket sprawl where we store tons, like terabytes of data. Sometimes this data is used, sometimes it's not used. We tend to ship most of our logs into these buckets, and these are put in sanity areas. And if we forget to put a lifecycle policy on this, it tends to get expensive. That is one of the cost drivers. And it applies same for AWS block store, like EBS volumes. So every virtual machine has a block store, like EBS volumes. You delete the virtual machine, but you don't delete the volumes. The volume is still available, but it's detached from the EC2 machine. But you are still being charged for the storage. The next one is RDS databases. The databases are like Aurora PostgreSQL or like similar such databases. Sometimes these databases are over provisioned with much higher IOPS. You don't need that scale of RDS databases because you don't have that much volume. We tend to over provision things because we expect the volume to grow someday, but that is a problem for the another day. The next cost driver is data transfer. So data transfer charges are often overlooked because they creep up in your AWS cloud. So think of this as in an organization, it's not just like one single account. You have 10 different accounts. Some are prod, some are non-prod. You have one account per team, and they have their own VPC, and they want to connect to another VPC in another account. You have the NAT gateways, you have the trust gateways, you do VPC peering, you do cross AZ transfers. There are multiple different layers of networking abstractions that that really blends this data transfer charges. You don't expect these charges to be like simple. There's okay, cut here. So the next one is data transfer charges. So the data transfer charges are the cost from network egress charges, which is if you have multiple AWS accounts in an organization and each account has its own VPC and you're trying to connect these VPCs using NAT gateways or VPC peerings, and you have applications in multiple different VPCs trying to continuously talk to each other, there's a charge for that. And these, if not controlled, these charges tend to be increasing. If there's, for example, there's a spike in the traffic from one VPC to another, you see a data transfer charges. The next one, the most probably, is the third-party services. So all the cloud providers provide third-party APIs through their portal, and basically they have their own subscription models. For example, you have Red Hat licenses for the EC2 machines that are provided through AWS account. Now, sometimes these licenses are managed through your cloud provider, but if not managed properly, these tend to add additional burden to your AWS cloud. So what are the common challenges? So these challenges are pretty much common over entire cloud architectures. One is over provisioning. So over provisioning means you're over provisioning compute for the application that it doesn't require. So you are giving excessive resources to the applications. And this causes, like, so for example, you have an application that uses like only 10% of the CPU and the remaining 90% of the CPU time is handled. That is over provisioning. The second one is lack of visibility. So resource usage is not often clear because it's easy. So the cloud providers make it easy for you to provision resources, and you don't see the impact of provisioning these resources immediately until you get a bill at the end of the month. So there's not an instant alert that lets you know that, okay, this action that I have taken is increasing the cloud cost. So the lack of visibility is often one of the common challenges. There's multi-cloud complexity. So most of the organizations are on single cloud provider, but there are other organizations that do multi-cloud, where some of these resources are on AWS and some of their resources on GCP. We had an instance where some of the engineers were working on a hackathon project, and it was like 3 years ago, and they forgot to turn off the instances in like the Google Cloud account, because most of our work goes in one single cloud provider. It's hard to keep track of all the resources in a multi-cloud environment. So resource managing techniques, right sizing. So right sizing ensures that the allocation matches the workload goals. So there are multiple tools that help us do this. And this works on various different levels. So for example, you have AWS tools like AWS Trusted Advisor, which lets you know, okay, these are the databases that haven't had connections in the past few days, or these are the idle instances that are not getting any traffic. These are the idle EBS volumes that are not attached to any EC2 instances. So the AWS Trusted Advisor is such tool that's really helpful for you to know which resources are not used anymore so that you can deprovision them appropriately. And also the right sizing, and when it comes to containers, so the right sizing, like for example, you have Kubernetes, and Kubernetes has limits and requests. So requests make sure that you have certain amount of CPU and memory, and there's a limit. So understanding how much your application needs, because you have the observability tools in the mix. So once you have these observability tools, you can say, hey, how much, this is the amount of CPU that I need. I don't need 1 gig memory and 5 virtual CPUs. I can just get by one virtual CPU and like 0.5 gigs of RAM. Now so understanding what your application requires and appropriately setting those configurations is right sizing. Auto scaling. So auto scaling is dynamically adjusting your resources based on real-time demand. And this is much more in practical scenario applied on various levels of abstraction. So AWS provides what's called as an auto scaling group, where like you can provision more nodes in the cluster, like automatically based on a certain threshold. So for example, let's just say you have 10 EC2 instances in an auto scaling group, and you have a spike in traffic because you're running some Thanksgiving promotion and you're expecting these traffic to go up, and you need more instances. Now, setting an auto scaling group and letting it expand, let the auto scaling group add more boards to deploy applications like horizontal scalability is called as auto scaling. And basically, you need to be aggressive with auto scaling. You have to set up proper thresholds, because once it's not just scale up, you should also scale down once the peak is over. The next one is instance types. So one of the instance types that I think all the cloud providers provide is like Spot instances. So Spot instances are like much cheaper than the regular instances, but they don't guarantee the availability. They come at much lesser cost, but they can be terminated at any point of time by your cloud provider. Now, these Spot instances are pretty much useful for various different tasks like CI/CD. You have like batch processing, where you have the one-off job where you want to process a bunch of records and you spin up these pod instances. The next one is reserved instances. So reserved instances are one, you know that you need a minimum number of instances in your auto-scaling group or your cluster. And instead of like dynamically provisioning it, you set, hey, I need this number of CPUs at all time. And that's when you go to your cloud provider and say, hey, I need this compute days, 24 hours a day. And that's when you go to the reserved instances to make sure like you get a long-term discount and of like that's the best for the applications that run 365 days, 24 hours. And the second one is on-demand instances. So the on-demand instances are used for short-term variable needs, as you all know. This is the most common type of the EC2 instances that we use in our cloud architectures. So one more thing I want to talk about here is the density optimization. So in containers and serverless models, you have a container that runs your application. You have bunch of very small, tiny containers that run on a single node. So thanks to Docker and Kubernetes, like deploying containers has become pretty much easy for everyone. And also like integrating Kubernetes has proven to be substantial cost savings for the cloud. One such thing is the density optimization. Density optimization means you include more number of containers per node. You provision one big node and basically deploy multiple small containers or configure your Kubernetes to deploy these applications on like a single node. So that is density optimization, like more number of pods on a single node. So this helps you like use less nodes, but also like you have like more number of containers. There's no idle CPU time or idle memory that gets wasted here. So the next one is node autoscaling. So the node autoscaling, as we talked before, it's similar to autoscaling group. You, as you get more and more demand, you add different nodes. So in the Kubernetes environments, we use Carpenter, one of the cluster, and also there is a cluster autoscaler which adds the nodes to Kubernetes. And also, there are some of the optimizations that you can do is execution times. So one of the thing is we want to see, like, for example, if there is a job, Kubernetes job that's running in a pod, and basically that pod is stuck in a flashback loop. Now we need to keep track of these restarts and make sure that those don't occur, because oftentimes this is a wastage of resource. So the single Kubernetes job is supposed to perform a job and then just complete it. The pod should die. And the other one is reducing idle times. So implement efficient cold start strategies to minimize idle costs. So whenever there's a new pod spins up, you have the application inside it running. The application needs to spin up whatever the JVM or other software that it needs to run. So we can do some strategies at the application layer to reduce the idle times. Next one is code optimization. So minimize dependencies and optimize code for better memory and CPU usage. You can take a look at the flame graphs, like see if there's any like potential memory leaks in your application and fix those. These are the smaller optimizations, but overall they compound to significant cost optimizations. The storage and data management. So one of the things that we can do for cloud cost optimization is implement policies to move data across storage tiers based on access patterns. For example, you have like a doc that you want to store for the compliance reasons, but it's not accessed frequently. So what do? You store it in a like less access tier, which is lesser cost. And basically you implement a lifecycle policy where an object, it might be a document or any other, it's a log file, like goes through a different phases of tiers and it's stored in like archived, like, and this helps you reduce like the storage cost for S3 or other object storage. Now, another thing that we can do is data compression and deduplication. So techniques like data deep compression and deduplication reduce storage needs, basically because you have a 100 TB file, you can just compress it aggressively to make sure that you have 10 GB or 20 GB file. The regular audits. So routine audits also help identify and remove unnecessary data. Sometimes you only want to store 7 years worth of data, and the data that's more than 7 years, you don't need it. So performing data audits on the data helps you like access, like reduce your cloud costs. Monitoring and cost visibility. So continuous monitoring. So continuous monitoring is essential for identifying unexpected usage spikes and tracking resource utilization trends. So this means that we need to always expect that if there is a spike, there's actually a bug somewhere that's causing this spike, and we need to set up appropriate monitoring and alerting to let us know that, hey, there's a spike. That means something, or there's a bug in production or other environments that's causing the spike. There's AWS cost visibility tools. AWS Cost Explorer is one such tool that helps us deep dive into what resources are we using, like what are the cost patterns, like how much we are going to be spending in particular month based on the current usage. And this gives us a visibility into how much the change in configuration can lead to the increase in cloud costs. So, and also we can set up budgets and alerts. So we can do spending thresholds on a particular AWS account. Let's just say we have $1,000 maximum budget on an AWS account running an example application. Now we can set up alerts when basically there is a spike, or when the forecast is more than the current budget, and we can set up alerts and we can fix what's causing what resources were that's causing these alerts to get fired up. There's cost allocation tags. So the cost allocation tags is one of the crucial parts of cloud cost management, because it lets you know which team, which project, or which department this resource belongs to, and how much it costs. Because it's all about unit economics. So how much, so for example, if you're doing a transaction of $100, how much you're actually spending for the cloud is what matters. So if you're making $100 on a transaction and you're spending $80 on a cloud cost, that's not a viable business model. FinOps. So FinOps is a cultural approach to cost. So FinOps provides a framework for cost management that integrates financial accountability into cloud spending. It just means that it's a culture shift where finance teams are more involved with the engineering teams. It's a shared responsibility between all the teams to make sure that we are operating the cloud effectively, and basically like at a lower cost. And this also, one of the principles of the FinOps is that the engineering teams should be able to know what are the repercussions of their actions of provisioning resources. And it should be near instant, or at least it should be like the projected cost should be like visible to the team so that they can take active steps to not cross their budgets, etc. And so this helps developers and the engineering teams know that, hey, I want to make a design decision, but cost is also one of them. So these are all the principles of FinOps, and implementing FinOps will help like organizations make like cloud use much easier. Leveraging AI and FinOps to drive cloud efficiency. AI-powered tools can continuously monitor cloud usage and expenses in real time. For example, you have all this data about billing and cloud usage, like how much cloud we're using, how much idle time, how much busy time. Now we can train some AI models based on the data that we collect. And based on that, we can design the tools that can say, hey, at this point in time, you are going to have a spike in load. And that way, so you can predict that you might need resources at certain point of time. And this helps team prepare for if they need any resources at certain point of time. Anomaly detection. So AI algorithms can also analyze historical spending data to detect cost anomalies and irregularities, allowing businesses to address these issues promptly. So there's always anomalies in the data. So it might be like, as I said before, it might be some bug that's causing a spike at one point of time or other. For example, there is, if you're the NAT gateway cost, so the data transfer cost, there's a spike, there's a huge bunch of requests that's going out, there's data that's coming in, there's egress data. And basically that's an anomaly because there's a misconfiguration on the network side that's caused this spike. Now, AI algorithms can detect this cost anomalies and attribute it to, hey, this change has cost this much to the organization. Eliminating inefficient resource use. So AI can help eliminate idle cloud resources and unused resources by automatically shutting down or resizing them, reducing wasteful spending. I'll talk more about this in the AI agentic approach. But yeah, let's move forward. Demand forecasting and auto scaling. As I already said, AI can predict the future demand for the cloud resources, enabling better planning and deployment, and dynamically adjusting resources to avoid over provisioning. Using prompt engineering for achieving cloud efficiency. This is what we've been waiting for. As you guys already know, like prompt engineering is how you talk to AI models to get the job. And one of the key things about the prompt engineering is role prompting. So what is role prompting? So role prompting is a technique in prompt engineering to control the output generated by the model by assigning a specific role to the AI model. This can be any model. I just used ChatGPT example here, but it can be Cloud, it can be Llama, it can be Gemini, or any AI model that's GPT based. So we can make use of roles like FinOps expert and craft prompts by providing more context to the prompt. Let's see a couple of examples. So some of the prompts using the FinOps expert role. So here, what I did try was, as a FinOps expert, can you please help deep dive into our AWS cloud bill? Please explain what is different, unblended costs, and amortized costs. So, as someone who is coming to like cloud billing, like specifically AWS cloud billing, there are multiple different types of costs. Like you have like unblended costs, you have amortized costs, and there are multiple different costs. So, to get you understand, AI models can definitely help you to do that. And you can use roles like FinOps expert to help you guide how to implement the FinOps best practices in your organization. This is one of the experiments that I did. So you can also use, as a FinOps expert, can you analyze our AWS invoice and let us know why our AWS bill was higher than usual? Can you please provide detailed report on how could we reduce our AWS spend? Now, this is a very specific prompt, and I'm also giving some context to the AI model so that it knows. I've also gave the invoice and let the AI model figure out like why was the spend increased in the previous month. So since we are talking on the same page, so one of the things that is popular is like most people are trying to get now is AI agentic approach. So AI agentic approach is like we build AI agents to get the job done. So for example, you can build an AI agent that would monitor the usage of a resource. Let's just say there is a resource that says, hey, this resource is been idle for a while. It's not even taking connections. Let me, shut down that server. I will let the infrastructure engineer know that this is happening, and I will let them, and I'll shut down the database temporarily. Now, this is what an AI agentic AI approach is. So we can build like simple AI agents. So there's two amazing resources. One is LangChain, one is Crew AI. They use prompts under the hood, the prompt engineering, so they can act as a part of automation, and they can talk to any of the AI models that are currently available, like ChatGPT, Cloud, or any other open source models. And basically, like, you build an AI agent that will help you implement these actions for cost optimization on your behalf. Let's get to the conclusion. So, cost optimization in cloud-native platforms requires a comprehensive approach that balances technical strategies with organizations' shares. It's not always easy. The cloud-native platforms are like increasing. There's a need for the cloud platforms that operate efficiently and at a lower cost. By understanding the primary cost drivers such as compute resources, storage, data transfer, third-party service organizations, we can implement like tailored techniques to reduce expenses without compromising performance. More resources is not equal to like more performance. That's true that you can run like a big instance and throw an application on it, but that's not how it works. Resource management practices like right sizing, auto scaling, and diversified instance types from the backbone of effective cost optimization. At the end of the at the end of the day, these are the core principles. Like, use how much you need, auto scale whenever you need, and use the right resources. That's it. And additionally, when it comes to container and serverless, make sure you use like limits and requests appropriately. Coupled with, when it comes to databases and block storage, use data lifecycle management, lifecycle policies, and to make sure that the data is stored securely and also in a cost efficient way. And also, like, I want to put a strong emphasis on monitoring, and cost visibility framework is really important because without adequate monitoring, you don't even know what resources you have, what are the spikes. So having a strong monitoring foundation, having a budget alerts, having proper utilization alerts will help you track resources even before the AWS cloud bill lands at you. So FinOps principles bring a cultural dimension to this strategy, encouraging cross-functional collaboration and fostering cost awareness within development teams. I would reiterate that FinOps will help business teams, finance teams understand the cloud expenditure with the help of the engineering teams. And also, the engineering teams would be responsible for the cloud costs and the actions that they take for provisioning new cloud resources. So, this financial accountability in every stage of cloud management, organizations can align spending with business goals, creating a culture of continuous improvement. Thank you. That was my talk for today. Hope you liked it. There's a great future for cloud cost optimizations using the agentic AI approach, which I'm truly excited about. Thank you, everyone. Have a good rest of your day.